Hello everyone, my name is Şahin Hüseynli. I am a PhD candidate in civil engineering at the University of Bristol. My supervisors are Dr. Flavia De Luca and Dr. Dimitri Karamitros. I have just started my PhD research on soil structure interaction, and in this congress I'm going to share with you my initial review of the dynamics SSI models. The importance of including SSI in the seismic design of structures is well recognized, and it has been shown that taking SSI into account under particular conditions may have detrimental as well as beneficial effects on the seismic response of structures. On the left, you see the collapse of Fuki Bridge, which is one of the most dramatic failures of the 1995 Kobe earthquake. Due to the SSI effects in the increase in the natural period of the bridge resulted in higher spectral demands and led to the collapse of the structure. On the right, however, you see one of the most remarkable structures, the Leaning Tower of Pisa. Despite its settlement, low strength, and low ductility, it survived several strong earthquakes without any damage. In this case, it seems like the increase in the natural period due to SSI effects have a beneficial effect on the seismic response of the structure. Therefore, to determine the most appropriate model for different engineering applications, we proposed an application-oriented classification of the SSI modeling techniques. The soil structure interaction has two main components: superstructure modeling, which also includes the foundation, and the substructure modeling, which is basically modeling the soil medium underneath the structure. There are several different approaches available for soil modeling. We have grouped them under two main categories: condensed and continuum modeling. In condensed modeling, total degrees of freedom of the system are condensed into elements such as springs, dashpots, and so on. In continuum modeling, however, the entire soil foundation structure system is simulated as a whole. Over the years, several condensed approaches have been proposed to simplify the substructure modeling, such as Winkler model, interactive Winkler models, Beamon nonlinear Winkler foundation model, impedance function models, and macro element models. There are also several continuum approaches available, such as the finite element method, boundary element method, finite difference method, and a combination of these. And in this presentation, I'm going to talk about the key aspects of each of these models. First, I'm going to talk about the condensed modeling techniques. I would like to start with the classical Winkler model. In this model, soil medium is idealized with a set of linear elastic springs, and the beam-on elastic foundation model that you see on the right is the simplest way to simulate SSI effects. However, in this model, the interaction between springs is not taken into consideration. Therefore, there are several improved versions available that I will talk about them next, but since application of this methodology is very straightforward, it has been applied in many research studies. The main challenge of this model is the determination of the spring stiffness, which is the only parameter that needs to be determined. But since the static and dynamic soil stiffnesses are of different orders of magnitude, it's challenging to determine that parameter. As I just mentioned, there are some improved versions of Winkler model. In interactive Winkler models, as you see in the figure, soil springs are connected with an interaction layer. But still linear pressure deflection relationship is used in these models, so the soil and foundation nonlinearity is not taken into consideration. There are several approaches available using this methodology that have been proposed over the years by researchers like Filanonka Borodik, Hetenyi, Pasternak, and so on, and they have been widely used in studies analyzing elastic SSI effects. But it has to be mentioned that in the presence of large strains, linear elastic model is not reliable anymore, and therefore there is a need for a nonlinear model. The nonlinearity is addressed in another variation of the classic Winkler model, which is called beam-on nonlinear Winkler foundation model. In this model, one-dimensional nonlinear springs are added to the soil foundation interface, and they are capable of capturing nonlinear soil and foundation behavior. But in this model, the variation of stiffness and damping with frequency is not considered. However, this model is still very widely used in research and practice because it's the easiest model that can capture nonlinear behavior in SSI problems. But due to its one-dimensional nature, only the effects of loads in the direction of springs are considered, which means that the loads that are perpendicular to them have no impact on the response. Although in BMON nonlinear Winkler foundation model, frequency-dependent characteristics are not captured, there are several approaches based on impedance functions that can capture this behavior. In these models, the soil medium is idealized with a set of springs, dashpots, and masses. Therefore, as I just mentioned, the frequency-dependent characteristics of the stiffness and damping are also being considered. But the main limitation of these models is that they are not able to capture the coupled interaction between the soil and the structure. There are several well-known approaches based on this methodology, such as lumped parameter models, Comb model, and so on, and these models are widely used in dynamic SSI problems. However, the calibration of the coefficients, such as spring stiffness, damping coefficient, and so on, is a bit challenging and not always reliable, and therefore it's not very suitable for complex SSI problems. I just mentioned that the main limitation of impedance function models is that they cannot capture the coupled soil structure interaction, but this behavior can be captured using macro elements. There are several advanced macro element models that can capture very complicated relationships, such as the soil nonlinearity and coupled interaction between the soil and structure. But in contrast to other approaches, this is a relatively new approach and therefore it has very little experimental validation. There are several proposed macro element models such as contact interface models, cyclic macro element models, and so on, but they are not yet widely used in practice. But it must be noted that using this methodology, it's still challenging to capture very complicated relationships, such as the foundation flexibility. Therefore, in very complex SSI problems, continuum models would be more reliable. Now I'm going to go over continuum modeling techniques. Among the continuum approaches, finite element method is the most well-known methodology, and it's able to capture very complicated relationships such as heterogeneous and nonlinear soil behavior, complex geometries, and so on. But this method is computationally demanding, which means that it requires significant amount of time and effort. Therefore, it's not suitable for ordinary practical applications, but it can be used for research-oriented contexts and the design of strategically important structures. Still, it has been noted that it's not very easy to apply this methodology to SSI problems, because there are so many challenges such as the selection of constitutive model for the soil, selection of the contact interface model, and the size of the mesh discretization, and so on. But in finite difference method, it's very easy to capture complicated relationships like soil nonlinearity. And also less modeling time and effort is required in comparison to finite element method. But only uniform grids can be used in the modeling, and therefore it's not possible to model complex geometries. However, due to its simplicity, it is widely applied to geotechnical problems, but it's not as commonly used in structural engineering practice, since capturing complex superstructure geometries is very challenging. Therefore, it's difficult to implement this methodology to SSI problems. Similar to finite difference method, boundary element method is another type of continuum approach that requires less modeling time and effort in comparison to finite element method, because in this methodology only surface discretization is required. However, it doesn't have same flexibility in modeling complex systems as finite element method. Therefore, in SSI problems, it's often coupled with finite element method. But it's possible to analyze SSI problem both in infinite and semi-infinite domains. However, capturing complex behaviors such as the heterogeneous and nonlinear soil behavior is very challenging using this methodology. So it can be noticed that every approach has their own limitations and challenges. Therefore, to benefit from the advantages and avoid the disadvantages of different continuum approaches, they are sometimes coupled together. Usually, the structure and the near-field soil is modeled with finite element method because those regions are highly nonlinear and high level of accuracy is required. Therefore, far-field soil, on the other hand, is usually modeled with a simpler method. This way, the application of continuum modeling also becomes more practical. The limitations of this methodology depends on the models that have been used, which are the ones that I just mentioned, but they are usually applied in research-oriented contexts, not in practice, because it requires significant expertise. In this research, we also reviewed a selection of recent comparative studies. In these studies, to demonstrate the impacts of SSI on the seismic response of structures, usually fixed base model results are compared against continuum and condensed model results. Also, in some studies, condensed model results have been validated against more comprehensive continuum model results. These studies may be useful for engineers to determine which methodology would be more appropriate in each case. And now I'm going to go over the main conclusions drawn from these studies. In terms of simplified condensed models, the most widely used ones are the variations of the classic Winkler model, and in particular the Beamon nonlinear Winkler foundation model. However, this does not account for the frequency-dependent stiffness and damping properties of the soil and foundation system. Therefore, it should be used with caution in the case of high-frequency excitations. Impedance function models are often used in dynamic SSI studies. Some lumped parameter models can simulate complex relationships while capturing frequency-dependent characteristics, but they are not often available in commercial numerical analysis packages, and therefore they are not regularly used in practical applications. It's also possible to model the coupling between the different directions of loading with the advanced macro element models, which can also accurately incorporate soil nonlinearity, but due to a lack of extensive experimental validation, this model is not yet widely used in practice. In terms of continuum modeling, the most widely used one is the finite element method. It can be used to model very complex forms of SSI, but it involves a significant amount of computational time and effort, so therefore it's not very suitable for ordinary practical problems, but only for research and design of strategic structures. The finite difference method is widely used in geotechnical problems because it's very simple, but it's not usually preferred in SSI problems because it's difficult to model complex structural systems using this methodology. The boundary element method is also easier to use, but it doesn't offer flexibility in modeling complex systems. Therefore, this method is often combined with the finite element method, but this hybrid methodology requires significant expertise, and therefore it's mainly used for research-related applications. So, it's obvious that there are already well-established advanced modeling techniques that can comprehensively simulate SSI behavior, but there is still a necessity for further research in this field to identify the optimal model in relation to specific applications. Therefore, in the end, I would like to briefly talk about the next steps of my PhD research. First, I'm going to model an experimentally validated substandard reinforced concrete structure, and then I'm going to add a soil model to my case study that's based on detailed geotechnical investigations. And then I'm going to carry out another comparative study using different approaches that I just discussed in this presentation. And my initial goal is to determine the impact of different SSI modeling techniques on the seismic fragility characteristics of substandard reinforced concrete structures. Thank you very much for having me in this Congress. I really wanted to attend in person, but unfortunately I couldn't make it. I hope you are having a good time in my hometown. Thank you for listening to my presentation, and I would be happy to hear your questions if you have any.